Ever stop and think about what's actually holding our world together? I mean, not just the big stuff, but everything. Today, we're going to pull back the curtain on the secret architecture of matter itself, from the tiniest invisible bonds all the way up to, well, us. Let's dive in.
Okay, take a look at this. You've got solid ice on the left, and you've got steam billowing out on the right. Here's the crazy part. They're both the exact same thing. Just water, H2O, that's it. So how on earth can the very same ingredient create two things that are so completely different?
And that's the big question, right? Same ingredients, but they build completely different worlds. What gives? Well, to get to the bottom of it, we have to zoom in, like way, way in.
All right, so let's start with the basics. Let's talk about our world of matter. What is it that actually makes a solid, and a gas,
Here's the first major clue. It turns out nothing is really standing still. Everything you can see and touch, everything, is made of these impossibly tiny particles. And here's the kicker. They are always, and I mean always, moving.
And how those little particles are moving and organized, well, that changes everything. In a solid, they're all locked in place, kind of shivering in a tight, neat grid. In a liquid, they're still buddies, they're still close, but they've got enough wiggle room to slide past each other. And then you have a gas, where they've totally broken free. They're just zipping around like crazy with tons of empty space in between.
So what's keeping them together? You got to think of it like an invisible force field, right? An attraction between all these particles. The stronger that force, the tighter they're going to huddle up. A solid is like a human chain where everyone's linking arms for dear life. A gas, that's more like a scattered crowd with everyone just doing their own thing. This invisible pull is literally what shapes our physical world.
Okay, so these rules apply to pretty much everything. But to really see how it all works, let's zoom in on one super important family of molecules. It is time for you to meet the hydrocarbons.
Hydrocarbons are, believe it or not, made of just two things, hydrogen and carbon. That's the whole recipe. And yet, from this super simple combo, we get the fuel that runs our cars, the energy that heats our homes, and the plastics that make up, well, almost everything around us. They are, without a doubt, the building blocks of modern life.
And this is where the real magic happens. So here's the process. You start with one of these simple little units. It's called a monomer. Then you put it under just the right conditions, a lot of heat and pressure, and bam! Thousands of them start linking together hand in hand to form this massive chain called a polymer. And just like that, you've turned a bunch of tiny, simple molecules into the tough, flexible plastic we all know.
But that brings up an even deeper question. If particles are held together by forces, what's holding the atoms together inside the particles in the first place? What is the actual, fundamental glue?
Well, that glue has a name. It's called a covalent bond. And it's not really a substance, it's more like an agreement. It's a deal where two atoms decide to share some of their electrons. And this sharing creates this incredibly powerful connection that locks them together into a single, stable molecule.
Now, here's a key detail. Not all bonds are created equal. We have something called bond order, which is really just a fancy way of asking how many pairs of electrons are they sharing. If it's one pair, that's a single bond. Two pairs, a double bond. Three, you guessed it, a triple bond. And this number changes everything.
And this table right here shows you exactly why. Just look at what happens. When two carbon atoms have a single bond, a bond order of 1, they're about 154 picometers apart. Now bump that up to a double bond, they're sharing more, so they get pulled closer, down to 133. And with a triple bond, they're practically hugging, at just 120 picometers.
So the takeaway is simple, but it is huge. The more electrons two atoms share, the stronger that connection becomes, and the closer they're pulled together. That simple rule, more sharing equals shorter and stronger, is what determines the shape, the stability, and the properties of pretty much every substance you can think of.
You know, the path to figuring all this out wasn't some straight line. Sometimes discovery takes a totally unexpected turn. Sometimes it even comes from a dream.
So for a long time, there was this one molecule that was driving chemists absolutely bonkers. It's called benzene. The formula looked simple enough, C6H6, 6 carbons, 6 hydrogens, but the problem was it was weirdly stable. It was way stronger than it had any right to be, and nobody could figure out an arrangement of atoms that made any sense.
And then, the breakthrough came from the most unexpected place. A chemist named Auguste Kekule was dozing off in front of his fireplace. He later wrote about this dream where he saw atoms twisting around like snakes, and then he saw one of the snakes grab its own tail and start spinning in a circle. He said he woke up as if by a flash of lightning. He had it. Benzene wasn't a chain, it was a ring.
And that wild dream led scientists to this incredible idea called resonance. See, it turns out the shared electrons in benzene aren't just stuck between two atoms. No, they're delocalized. They're smeared out, shared equally among all 6 carbon atoms in the entire ring. This creates this ultra-stable hybrid structure, and it finally explained why benzene was so tough to break.
So, let's put it all together now. Let's trace the complete path from the tiniest bond all the way up to our own reality.
It's really just a beautiful chain of logic when you see it laid out. It all starts with atoms sharing electrons. That makes covalent bonds. Those bonds build the atoms into specific molecules. Then those molecules feel an attraction to each other, these intermolecular forces. And finally, the strength of those forces is what decides if you end up with a solid, a liquid, or a gas. It all starts with that tiny shared electron.
So there's our answer. Ice and steam are so different because of the strength of the forces between their molecules. And those forces are all a result of the fundamental bonds within them. It all connects, which leaves us with one last really exciting thought. If these invisible bonds truly are the architects of our reality, what incredible new worlds could we start to build just by learning how to rearrange them? The possibilities are really something to think about.